Dyes and stains have long been used to detect and visualize structures and processes in biological samples. Today, many of the favored dyes and stains have a fluorescent component because fluorescent molecules can be detected with extraordinary sensitivity and selectivity. This tutorial will give you a basic introduction to the fluorescence process and definitions of some key terms that you will encounter as you learn more about fluorescence. Examples of some widely used fluorescent dyes are ethidium bromide, alexafluor dyes, and fluorescein. How and why do these dyes and stains emit different colors of light? Some molecules are capable of being excited via absorption of light energy to a higher energy state, also called an excited state. The energy of the excited state, which cannot be sustained for long, decays or decreases, resulting in the emission of light energy. This process is called fluorescence. To fluoresce means to emit light via this process. A fluorophore is a molecule that is capable of fluorescing. In its ground state, the fluorophore molecule is in a relatively low-energy, stable configuration, and it does not fluoresce. When light from an external source hits a fluorophore molecule, the molecule can absorb the light energy. If the energy absorbed is sufficient, the molecule reaches a higher energy state called an excited state. This process is known as excitation. There are multiple excited states or energy levels that the fluorophore can attain, depending on the wavelength and energy of the external light source. Since the fluorophore is unstable at high energy configurations, it eventually adopts the lowest energy excited state, which is semi-stable. The length of time that the fluorophore is in excited states is called the excited lifetime, and it lasts for a very short time, ranging from 10 to the minus 15 to 10 to the minus 9 seconds. Next, the fluorophore rearranges from the semi-stable excited state back to the ground state, and the excess energy is released and emitted as light. The emitted light is of lower energy, and thus longer wavelength than the absorbed light. This means that the color of the light that is emitted is different from the color of the light that has been absorbed. Emission of light returns the fluorophore to its ground state. The fluorophore can absorb light energy again and go through the entire process repeatedly. The cyclical fluorescence process can be summarized as 1. Excitation of a fluorophore through the absorption of light energy. 2. A transient excited lifetime with some loss of energy. And 3. Return of the fluorophore to its ground state, accompanied by the emission of light. The light energy emitted is always of a longer wavelength than the light energy absorbed, due to the energy lost during the transient excited lifetime, as shown in Step 2. A fluorophore can repeatedly undergo the fluorescence process, in theory, indefinitely. This is extremely useful because it means that one fluorophore molecule can generate a signal multiple times. This property makes fluorescence a very sensitive technique for visualizing microscopic samples. Even a small amount of the stain can be detected. In reality, however, the fluorophore's structural instability during the excited lifetime makes it susceptible to degradation. High-intensity illumination can cause the fluorophore to change its structure so that it can no longer fluoresce. This is called photobleaching. When a fluorescent sample, such as a slide with mounted tissue, is photobleached, the fluorophores are no longer promoted to an excited state, even when the required light energy is supplied. Now that we've introduced the general process of fluorescence, let's take a look at the light spectrum and its importance in fluorescence. The visible spectrum is composed of light with wavelengths ranging from approximately 400 nanometers to 700 nanometers. Light waves with shorter wavelengths have higher frequency and higher energy. Light waves with longer wavelengths have lower frequency and lower energy. As we stated before, an excited fluorophore emits lower energy light than the light it absorbed. Therefore, there's always a shift along the spectrum between the color of the light absorbed by the fluorophore during excitation and the color emitted. For example, let's say that we have a tube that contains a particular fluorescent dye. If we shine 480 nanometer light at the dye solution, some of the fluorophore molecules will become excited. However, the majority of the molecules are not excited by this wavelength of light. As we increase the excitation wavelength, say to 520 nanometers, more molecules are excited. However, this is still not the wavelength at which the proportion of excited molecules is maximal. For this particular dye, 550 nanometers is the wavelength that excites more fluorophores than any other wavelength of light. At wavelengths longer than 550 nanometers, the fluorophore molecules still absorb energy and fluoresce, but again in smaller proportions. The range of excitation wavelengths can be represented in the form of a fluorescence excitation spectrum, which looks like this. A fluorescent dye absorbs light over a range of wavelengths, and every dye has a characteristic excitation range. However, some wavelengths within that range are more effective for excitation than other wavelengths. This range of wavelengths reflects the range of possible excited states that the fluorophore can achieve. So for each fluorescent dye, there is a specific wavelength, the excitation maximum, that most effectively induces fluorescence. Now let's look at the light that is emitted by the fluorophore molecules when they are excited at the optimal excitation wavelength. Just as fluorophore molecules absorb a range of wavelengths, they also emit a range of wavelengths. There is a spectrum of energy changes associated with these emission events. When we excite the previously described dye solution at its excitation maximum, 550 nanometers, light is emitted over a range of wavelengths. A molecule may emit at a different wavelength with each excitation event because of changes that can occur during the excited lifetime, but each emission will be within the range. Although the fluorophore molecules all emit the same intensity of light, the wavelengths, and therefore the colors of the emitted light, are not homogeneous. Collectively, however, the population fluoresces most intensely at 570 nanometers. Based on this distribution of emission wavelengths, we say that the emission maximum of this fluorophore is 570 nanometers. The range of wavelengths is represented by the fluorescence emission spectrum. The summary points of this introduction to fluorescence are: 1. Fluorophores are molecules that upon absorbing light energy can reach an excited state, then emit light energy. 2. The three-stage process of excitation, excited lifetime, and emission is called fluorescence. 3. Fluorophores absorb a range of wavelengths of light energy and also emit a range of wavelengths. Within these ranges are the excitation maximum and the emission maximum. Because the excitation and emission wavelengths are different, the absorbed and emitted light are detectable as different colors or areas on the visible spectrum.